We will start off with an overview of space science in 2012. And it is not easy to find a suitable person to do this, but the organizers were able to find a top-level person. It is Professor Ehud Behar. He is the director of the Asher Institute. The Asher Institute, you probably heard the name, it named several times during this Congress, belongs to the Technion in Haifa, and it is one of the world-class institutions. Professor Behar is an astrophysicist. He is also world-class. He is an expert in black holes, active galaxies, supernovae, dark matter. He uses space very actively, in particular for his observations in the X-ray and gamma-ray spectral region. So he uses X-ray observatories like the NASA spacecraft Chandra and ESA's XMM Newton. Professor Behar will give us an overview of the space science in 2012. Please come up and take the floor.
אחר הצהריים טובים לכולם. בקשתי לתת את ההרצאה בעברית, כך אני אעשה. כשאני אומר סקירה של תוצאות
of results and discoveries in science, I don't purport to cover all of science, but rather talk about the interesting astrophysical discoveries. We are using satellites very similar to the ones you've heard of. However, most of you are looking in the wrong direction. We are looking up. We started in this tradition, and I'd like to thank the Fisher Institute, which gives more and more room for science in its conferences. Everywhere in the world, science is one of the main engines driving science engineering, science research, enthusiasm of youngsters about space. All these things are our bread and butter, and it's very nice to come to a conference of scientific lectures as well. So it's an honor for me to provide an overview to start this session. Those of you who remember, I did the same last year, and you'll probably see that science develops fast. It's very difficult when you want to provide an overview of a whole year to find the highlights or to choose the highlights. So here are the 5 topics that I chose. The first has to do with planets. Studying planets is a hot topic in astrophysics in Israel as well. And I'll describe a planet that was discovered, which is very near Earth, right in our neighborhood. I'll describe a type of planets or star systems which have just been discovered, and that's systems of 2 stars with planets revolving around them. I'll go from the small size of planets to the bigger sizes of galaxies. This year we had 2 records in galaxies. I'll describe the record of the furthest galaxy, and you'll soon understand why this is so important and interesting. The first galaxies formed in the universe. And I also talk about the largest galaxy discovered this year. Then I'll talk about one of the most interesting topics that I know, and that's black holes. Black holes are very well known to astrophysicists already. We're convinced that they do exist, and I'll show you one of the most decisive proofs for this, and we are now analyzing them and categorizing them by size. Last year we had some experience with small black holes, giant black holes, and for some reason, however, we don't find holes of the middle range for some reason. And the 5th item on my list has to do with a very dramatic collision of a cloud that looks as if it's crashing into the center of our galaxy. Apparently there's a black hole there, and I'll show you pictures from that event, and in the next year or so you'll probably hear more about it. It's very dramatic. Since, after all, I'm a professor of physics and part of what I make a living of is teaching physics, I'll try and teach you some physics as I go along without you noticing it, so that you'll understand how we measure these things and see these beautiful things that I'll show you. One of the main methods, the most popular method for finding planets has to do with the Doppler effect. Planet orbits around its star, and even though the planet is much smaller than the star still feels it a little bit, feels the gravitation, the gravity of the planet. And when as the planet revolves around the star jogs a little bit to and fro, and this very slight jog is something that we can measure using Doppler effect. As the planet draws further, we see a redshift, what we call redshift, and then when it goes the other way, there's this blue shift. So you can see this back and forth that the planet is back and forth movement the planet is doing, or rather the star is doing, and that's one of our methods. Usually we find a planet not with direct view, but rather using all kinds of roundabout ways to notice that there's a planet there. So for several years, in fact, the Alpha Centauri planet system was being observed. It's only 4 light years away from Earth, and it's a system which is well known to us already. It can see in the naked eye as well. And what we can see is that there are 2 stars there, not just one. And looking at those 2 stars, if you look at it hard enough and long enough, then this year there was a study that showed that around the second star there's a planet which is about the size of planet Earth. Now, this is very unusual. Usually, because of the Doppler effect, it's easier to locate a larger planet, such as Jupiter, for example, but the size of Earth, that's very difficult to find. And I like to show you this result because it shows you the level of precision. You know, people think that astronomy is something like pick up a telescope and see nice pictures of stars, but this is something very different. So we have a system with 2 stars, and the smaller one has a planet around it, which means that there's a lot of gravity in this system. And first of all, you have to neutralize the effect of one star revolving around another, and then you have to neutralize the fact that the other star is revolving around itself, and all these magnetic fields and magnetic activity, because that causes the Doppler effect as well. And only after you clean up all these effects, which are much larger and more significant, then you can see this effect that you can see here, and I'm showing you this with a mouse, of acceleration going up and down. I don't think you can read the figures, but it's 0.5 meter per second. It's on that scale, 0.5 meter per second, that the second star fills and goes slightly forward and slightly backwards. In physics, astrophysics, we usually talk about 7 kilometers per hour, and this is a system 4 light years away, where astronomers or physicists were able to measure 0.5 meter per second. What's not so nice about this planet is that it's really very near to its star, about 4% of the distance between us and our sun, which means that it's terribly hot. No one can be there without getting burned, and therefore apparently it can't support life, even though from the size point of view it's very much like Earth. Another way of locating planets, which is indirect as well, is when there's an eclipse, a transit in astronomers speak. And when we measure the light emanating from a star, you see it decreasing just a little bit, as you can see from the Kepler telescope, NASA telescopes, and then you can tell that there was something passing just before the star. And if you are astronomy fans, then you know that we had this event that we held around the Venus eclipse. We see the passage of Venus against the sun, and here are the happy students, and this is Venus, very small. So it's a very small effect, about 1 promille. So only 1,000th of the light is detracted, so you have to take very accurate measures And that's why NASA decided that it should be done out of the atmosphere, and so that we are absolutely certain about it. This system with the 2 stars is called Kepler 47. Kepler just measures, does a lot of measurements and finds many candidates for solar systems and planets. There are many objects there. And what you can see here is an eclipse. It's very difficult to draw conclusions from a single eclipse, and that's why if you have a planet around a star, you want to see another eclipse and then another few transits. So you can see the light decreasing. I don't know if you can see the scale, but the number is 0.998. That's 2,000th. And you have to be very accurate to observe that. And here it comes again, and you can see now there's another, the other star also in transiting across the first star, the leading star. And this is a planet which is at the right distance from its star, like Earth is from the moon. We call it an astronomical unit. It's a good distance because it allows water to be in a liquid state, at least part of the time, and we believe that that's one of the prerequisites for life. So here's a planet which is exactly at the right distance. Unfortunately, it's not solid. Unlike Earth, it's a gaseous cloud, and life as we know it apparently can't develop on such a system. But if you follow the news on astronomy, we are closing in on those planets which are the right size and in the right place, and apparently perhaps we'll eventually find the right people on some of those planets, but we're not there yet. These circumbinary systems are very interesting. You can see an illustration from a NASA film for this Kepler 47b system. It shows you the system and where it is in the sky as well. And the Kepler detectors that you can see here gaze, someone said today we're looking downwards and gazing into space. This is very much what astronomers do, and you just look at those stars for many years and see if something interesting happens, if planets pass by. And Kepler does see a lot of those, and occasionally you see a planet in transit. So here's an illustration of 2 stars right next to each other. The planet is much further away, and it's at the right astronomical distance. If we were living on such a planet, then we would have seen the 2 stars setting, if you remember from Star Wars. Now, Star Wars fans will not be surprised by it, but for those who aren't, it's still very impressive to see the setting of 2 suns. Let's move on to bigger systems. So let's look at the universe as a whole, the largest system that we know. In this chart, there's a very short history of the universe. This is the Big Bang, and then there was a period of darkness after the Big Bang. And here colors start appearing. This is those of you who are believers and also believe in astronomy will think of it as let there be light, and that's when the first galaxies started. So this transition from a completely dark universe to a universe with galaxies and stars is very dramatic in cosmology, and that's why astronomers try very hard to find the very first galaxies formed. In theory, there's a large span of time, range of times in which this could have happened, and that's why you make observations. Usually you recognize them through or thanks to the redshift, that Doppler effect, even though here it has to do with the fact that the universe is expanding. So the ones which are further away are shifted much towards the red, and the reddest objects that you see on the telescope actually can only be identified through the reddest filters. This is the way to find the most distant galaxies. They're very pale. They emit very little light. That's why you have to use the most sensitive telescopes. Here, the Hubble will be used. You probably all know it. And not just the Hubble, but rather the deepest field that Hubble has. It has a field in the sky that it gazes into for a long period of time in order to develop high sensitivity for very pale objects. And there, a galaxy was found. We still have to verify its age, but as of Our current measurements, it's a red shift of about 12. That's 380 million years after the Big Bang. That's very early in the history of the universe. Today we're at 14 billion. The universe was just a very small percentage in age of its current age. And you can see in these very beautiful pictures by Hubble, done through the various filters, and you can tell when the first galaxies were born. In galaxies, we also had a record galaxy in terms of size this year. Here you can see a combined picture of the two NASA telescopes. One is the Hubble and the other is we had the GALEX, the ultraviolet, and Spitzer. This galaxy, which was well known, is not very distant. We have known it for some time. However, it doesn't end here where we can see it, but rather continues all the way over there. And ultraviolet, what you can see are young, very hot stars, which means that this galaxy is active and still creates new stars. GALEX, unfortunately or fortunately, you'll soon understand why, NASA got tired of it last year and decided that it's finished its role, and NASA is undergoing processes of privatization and partly opening its resources to the public at large. And NASA decided that they don't want to use this telescope, but they decided to allow others to use it. And there's a consortium of universities led by Caltech, which also was one of those who built this telescope, got the rights to use it. And there's an interesting Israeli spin here. That's why I'm telling you this. A few universities in Israel, the Weizmann Institute, Tel Aviv, and the Technion were part of this consortium, and in fact bought for good money this telescope for 2 months. So for 2 months we could do whatever we wanted with the NASA space telescope. The NASA chose not to use anymore, and right now we're working on the data. We got a lot of data, and otherwise under any other scenario it would have been very difficult for us to obtain those data. As for black holes, as I said, we know small black holes as large as a star, perhaps 10 times as large as a star, a few times the sun mass. And we know huge, gigantic ones, which are in the center of galaxies. By the way, we think that in the center of every galaxy there's a giant black hole. However, it turns out that black holes seem to start small and then grow. So what about all the adolescents? We have the young ones and the old ones, but what about the middle-aged ones? So for many years this was unclear. Lately we have started seeing the following phenomenon. Inside galaxies, not in the center, but those two violet dots here, or purple dots, they're objects which are particularly bright when you use X radiation, and they have a certain amount of mass which is not like the millions that we have in the center of galaxies, but they were identified by a new telescope which is which specializes in high energy, and it's actually a telescope that was sent into space, folded up, and then ejected a boom, a 10-meter boom, which separates the camera and other systems, which means that you get better separation, better so the camera is separated from the mirrors. NASA and ESA want to do it in with the two different satellites, formation flying. The Technion is also dealing with that, so that's one approach to the solution. So it's a single satellite, but the device is on the two sides of it, and in the middle there's only a structure holding them both. So X-ray waves mean just nanometers, and that means that the optics should be very stable at a distance of nanometers, and so that's another major success. More middle-sized mass black holes. Here's some Israeli news. This was published by the Technion this year, to do with centers of galaxies. Usually, as I said, we're talking about millions of sun masses, solar masses. One of our ways to weigh them is to look at the effect of their gravity on the environment. So if you look at all kinds of things around the black hole, you can measure the resonance. You see the light being emitted from the immediate environment of the black hole and reflected back to us from an object which is far away from the black light. And since we know the speed of light, we can calculate the distance of that object from the black hole. You can't see it with a telescope and you can't separate it, but you can use Doppler measurement to calculate it, and speed and distance can tell you what the mass is. This is how we measure the mass of the sun, by looking at the Kepler effect around the sun. So you weigh the mass of the black holes. We did it using a telescope in the Ramon Observatory in Israel, telescope belonging to the Tel Aviv University, and we found out of all this red spot which is off the charts. And that's a nice, interesting discovery, because it gives us an indication that, yes, there are black holes which are somewhere between 10 and a million solar masses. The last highlight that I want to show has to do with the black hole in the center of our galaxy. In the center of the Milky Way, there's a huge, gigantic black hole. And we know that there's a black hole there, not because it's active, it doesn't emit anything, but rather when you look at the stars revolving around it, then you can tell. This is a film which is taken, quote unquote, over 10 years. There are stars revolving around this black hole in the center. There's a cross here, you see, the center of the galaxy and the stars. I'll run it again. It won't move. So what it just showed you was the stars moving around the center of the galaxy. And using very basic gravity calculations, we can conclude that there's a very big mass in the center, some 4 million solar masses, 4 times the mass of the sun. Oh, now it's running. So you can see it zooming forward. There's this particular star that goes near the cross where the black hole is, and then it sort of zooms back, which means that there's a very strong gravity there. So this is nothing new, but what is new is that there's a cloud, not one of the stars, but rather a cloud which is somewhere in the vicinity of the black hole, and is drawing nearer to it. So here's the yellow cross again, representing the black hole. And here there's a cloud which, with the different colors, after every 2 years, you can see where it is. So 6 years ago it was here, 4 years ago it was here, and 2 years ago it's already very near. And down here you see charts trying to predict its trajectory, its course. This is that star revolving around the black hole, and this is true as of 2012. But when you extrapolate, you can see that this cloud is just about to collide onto the black hole. And if you look at the speed that it's going to gain while descending on the black hole, we have measurements until now, but the prediction is that it's going to take a huge drop right into this gravitational pit around the black hole, some in 2013, so it's going to be very interesting next year, or this year. Why? Because then when you come nearer the black hole, the gravity becomes very strong, and then two things happen. First, the black hole crashes the cloud, and you can start seeing it here already. Here's the star there, and the cloud as it was pictured in 2008, and here it starts integrating, and this is a map of the speeds of velocity, and here you can see that velocity is increasing here, so it's accelerating towards the black hole. High school physics is enough to understand this. It starts dropping, and you get some more energy, just like in a hydroelectric plant, you know. Waterfall gives you energy, so you can't. There'll be a lot of energy release here, which means that a lot of light will be emitted, probably in short waves such as X-ray and ultraviolet, and that's why you need telescopes in space to measure that. However, that will make our galaxy, which is relatively very quiet, the center of our galaxy is very quiet because nothing drops into the black hole, into an active galaxy. And if our predictions are right, then in this in this year we're going to have fireworks right out of that black hole. I think my time is up. So just very briefly, let me recap. We'll continue with astronomy, continuing to find new planets nearer our own and more similar to our own, more and more interesting. We found some very near ones, 4 light years. That's as near as you can think of outside the solar system. And we found some planets in the second binary systems as well. And we start thinking that perhaps some civilizations see multiple sunsets during the day. We are beginning to decipher the very first steps taken by the universe, the first galaxies, the first stars. And we are already getting near the very first percentages of the universe life, and in black holes using X-ray telescopes that you have to send out into space, where I make a lot of my living of. We are using them to see more and more black holes, and last but not least is our very own black hole in our own galaxy. Up until now it was dormant, but now it seems very promising. So there's a lot to look forward to, and I want to the thing is that even though we have a beautiful country, the rest of the universe is also worth a good look. Thank you.
Ehud, this was great.
זה היה נפלא.
You not only gave us a
לא
very
רק שנתת
comprehensive
לנו
overview of
סקירה מאוד
science in the past year, but you did it in such a way that you could transfer the fascination of space astrophysics to the audience. And I'm quite positive that there are a few people in this audience that have just made up their mind to become astrophysicists in their future life. Thank you again.
Thank you very much.
So the next talk here is entitled Science on Board ISS, A Look into the Future. The speaker has approached me on the corridors and he said, don't make a long introduction for me. Just introduce me as Randy Resnick, pilot. So I will not tell you anything about his bio. I will not tell you that he spent 259 hours in space with several extravehicular activities. I will just introduce him as Randy Resnick, pilot. Here you are.
Well done, thank you. We'll go to function F7. Function F7. Do the bottom one. There we go. Good afternoon, everyone. It is a pleasure to be here to join you at the conference as we celebrate as we honor and celebrate the lives and the legacy of Ilan Ramon and all the crew members of STS-107. From what you can see, Ilan Ramon didn't plan on being an astronaut. He was a pilot. He loved flying. And even though I never had the opportunity at NASA to meet Ilan, I felt like, I knew of him because, like him, all I ever wanted to do was fly. I was an F-18 pilot in the Marine Corps and became a test pilot and looking to fly anything I could get my hands on, because to me, a new airplane or aircraft was like making a new friend, and I just enjoy it all the time. But whatever I flew, unfortunately, none of them ever could reach escape velocity from Earth and reach orbit. So I had to apply for NASA and was selected in 2004. 2008 I was assigned to the STS-129 crew. On the 16th of November 2009, we launched off on the Space Shuttle Atlantis up to the International Space Station to take up 2 pallets and about 30,000 pounds of equipment that would be able to be used for the continued construction of the space station. But we're here to talk about science today, and the space station, ever since it became habitable 12 years ago, it has been a place where researchers from around the world have been able to come, conduct science and research that benefit all of us here on Earth. For those that aren't familiar how big the ISS is, as you can see, it's the size of an American football field. So it's massive. It's on the inside, the interior volume is like a big 5-bedroom house. So it's very comfortable for a crew of 6 to be up there. But it's up there every day of the year, orbiting 220 to 240 miles up, conducting science and figuring out how humans can live in space for long duration. We've talked over the past couple of days a lot about the engineering achievement and the international cooperation achievement. Today we're just take a little bit of time to talk about some of the research and science achievements that have been taking place on the ISS. As you can see, some of the disciplines that go ahead and are actively used up and expanded on up on the International Space Station. The interesting thing about all these disciplines, why do we do it on the ISS? Well, it's a completely unique facility in microgravity because stuff does not behave in microgravity the way it does here on Earth. And here's an example. This is astronaut Don Pettit putting an electrostatic charge on a knitting needle. Then he goes ahead and injects some water droplets around the knitting needle. Well, the water droplets should just shoot off in the vector that he placed them, but here they are being affected by electrostatic charge. Not something we can replicate here on Earth. So there's lots of different areas we can kind of classify the science. Here's the 3 areas we'll talk about today, but as you can see, and you'll see in the details, there's a lot of overlap amongst these 3 different areas. We'll start off talking about the Earth benefits, the stuff that we can see more tangibly here on Earth. First one, thinking about an ultrasound. If you have to go get an ultrasound, you have to go to the doctor's office, and there has to be an ultrasound technician that does the ultrasound. Then the doctor goes ahead and looks at the results. Well, what if we were able to take ultrasound machines and have them out remotely? And you're able to maybe call up the doctor. He could talk you through it remotely. You know, this is the telemedicine concept. And you could actually get the ultrasounds done. The doctor sits in one place, has all these different patients, send in the data remotely to him. He could be a lot more effective, a lot more cost effective, and also help people out that can't get to a doctor's office where there's an ultrasound machine and technician. We also had robotics on the space station that have allowed us to miniaturize and make better robotic machines here on Earth. The magnetic resonance imager, the MRI, that is so critical in medicine to getting crucial details for diagnosis. It gives real-time data, but everybody knows it's the really small area that you get put into on the slide, and it's very confined. Well, they've developed a robotic arm due to the work on the space station that was small enough and dexterous enough to be able to go and do the surgery while a patient was inside the MRI. Also developing the capability to have the robotic arm made out of things that obviously are not magnetic, because otherwise they interfere with the imaging. Simple things like we have satellites to take pictures. We've heard a lot about that for intelligence. But the one thing that the International Space Station gives you is the flexibility for when you have things like natural disasters or any other types of events of a crew member that can go over and take pictures with very different lenses, different optics, and other things that make it a lot more flexible than if you had just tasked a satellite to pass over that particular area. Things like vaccines. You know, the salmonella illness in the U.S. alone makes about 15,000 people sick and about 400 people die every year. Well, we took the virus up onto the space station and found out that it's a lot more virulent on the, up in microgravity. With that being said, they were able to actually find the controlling gene, and now they've got a vaccine, candidate vaccine that's a lot more likely to be able to allow us to survive salmonella. You heard astronaut Satoshi Furukawa speak earlier about the protein crystal growth. On the left side, you have a picture of the growth here on Earth. It gets fragmented because of gravity, and then you have the crystal that has grown up on orbit. The interesting thing about the one on orbit being more perfect, being bigger, over on the right side, you see where they mapped out the molecules of the protein and found, only because they did it up in microgravity, that extra water molecule. And with that water molecule figured out Remember when Satoshi talked about the keyhole in the key, they're able to make a much more direct and more effective vaccine for the illness. We've also got, you can see on the right side of the picture, the flames burn differently in space. And so they're able to make, pollution emissions to try and reduce those, and better efficiencies for actually burning combustion. Then on to the discovery things. We just had a great brief by the professor, and Satoshi mentioned the MAXI capability up on the ISS. Well, the MAXI is actually a capability that just stares out into space, and as soon as it sees something, what they do is alert via the internet, all the different astronomical observatories around the world, so that everyone can turn their telescopes towards that particular area and get the detailed data, so they can build the 3D picture of what happened. And the bottom left portion of the picture is what you see up there, is actually the first time that they were supposedly able to see a supermassive black hole destroy a star, something that had only been theorized previously. Obviously, the alpha magnetic spectrometer went up on the STS-134 on the last flight of Endeavour, and it is able to measure physics particles in space, that you can get the direction, you can get the energy of it, and this is stuff that was only previously possible in high energy accelerators in laboratories here on Earth. Never have we been able to collect particles in the wild, in their environment, and that's why the AMS is so important. The best part about AMS is we really don't know what we're going to get and the results that we're going to get from it, and that's the extreme edge of research and science and discovery. Then there's also the exploration side of what's going on with the science on the space station. How are we going to go ahead and take humans and go on long duration journeys throughout the solar system or throughout the galaxy? We've got a problem with bone loss. You see on the top left, you can see normal bone density, and what's the one picture below it shows what it would look like if someone had osteoporosis. Well, it turns out that about 1 month on the space station is equivalent to about 1 year with someone with osteoporosis here on the ground. So that's obviously pretty degenerative. But through the countermeasures, through exercise, through vitamins, and all the different things we're trying to figure out, we can slow and hopefully stop this, so that when we go to another planet, we don't reach it not being able to do work because our bones are so brittle. And there's also other ways to exercise while you're on the ISS. There's all kinds of things you can do that you just dreamed about previously. You don't necessarily have to play ball with just balls. Our very expensive Nikon cameras were always fun to play with. But eventually you get some time off, because that's necessary. You can break out the ball and play some football. But we also had, up on the ISS in the top right corner, you'll see some materials experiments. Basically big suitcases that we'd take out there on EVA, we'd open them up, and on the inside there were just dozens and dozens of particular different materials that we would leave out in space, and then another EVA would come pick it up much later. And through that exposure to the space radiation environment, we'd be able to see how it affected all these different materials and coatings and things. And that results of that are things that allow us to basically build satellites and space equipment quicker and cheaper, because we know what's going to work. And we're also able to put it on things like Curiosity, which you'll hear about in a few minutes from John Grunsfeld, and protect it while it's doing its job on Mars. And think about all the satellites that are being created here in Israel that eventually they run out of fuel or they stop working. Imagine if we could robotically figure out a way to send a robot up there to refuel it, repair it, instead of just building another satellite and trying to launch them. Because we all know that whether you launch going east or going west, it's expensive to get that mass to orbit. We also have a problem with your eyes degrading while you're in space. We think due to interocular pressure being increased. And so that's a problem if you're going on a long duration mission. So we're doing a lot of research to figure out what's causing that, and that may have results that'll help us back here on Earth for people that have problems with their vision. And also, water doesn't behave like it does here on Earth. You can see how surface tension holds it together in a big ball. And once you put an energy on it, the surface tension isn't able to hold on to the water, and it secretes itself. And that leads to some of the fluid work that's being done. On the right side, you can see how that purple fluid surface tension holds it to the walls. And so if you think about having your car or your gas tank and it takes the fuel from the bottom of the gas tank, because gravity holds the fuel down, you don't have to worry about running out of gas if there's any gas in it. Well, what if you're in gravity, zero gravity, and you don't have your fuel intake in the right spot? The fuel could be floating anywhere, and now your fuel intake's uncovered. So that is something that we have to work on for our engines and be able to figure out how to feed them with fuel and make our quantity indicators accurate. We're also now going to put up someone on the ISS for 1 year. If we're going to go anywhere like Mars or a near-Earth asteroid, there's going to be long journeys. We do have experience because we've had 4 Russian cosmonauts on the Mir space station spend over 365 days. But what's different now is that the habitability and the countermeasures for people is different, and there's been a lot of improvements since then. And with the partnership with the international partners, we're going to be able to get a lot more data by having an American crew member and a Russian cosmonaut spend over a year up there. Now, you think, when you're up in space, it's serious work. You're doing all this science, and this is what a crew should look like. Hopefully, after the 1 year duration experiment, we don't have a crew that looks like this. An important part of going outside of low Earth orbit is the fact that we got to take everything with us, and food is heavy. And so, if we can figure out a way to create our own food en route, that's going to be a lot better for us in the long run, because we'll be able to have more important stuff on board than just the food. Same thing applies for our what we call consumables. We need water, we need oxygen to breathe. And up on the space station, we're reclaiming about 75%, and we're improving every day the amount of water that we have. So we process the urine, we take the humidity out of the air that we breathe out in, and we're able to get about 75% back. We're able to take the electrolysis, take the water and separate it and make oxygen and hydrogen. And then we're working on the Sabatier process and being able to take the CO2 that we're breathing out and combine it with the hydrogen to make water and methane. So imagine the utility here on Earth if you've got, some place that might have a limited access to water. If they could reclaim 75% of the water they've got, that makes you a lot more viable in the area that you're at without rainfall. But all these self-contained regenerative environmental control systems are great for spacecraft, but they're also very useful here on Earth. And these things that I've shown you in all these different disciplines are only just a few of the hundreds and hundreds of experiments and science research that's going on board the space station right now. The other part about the space station in the future is that the U.S. Congress basically said they wanted to open it up to more than just NASA and its researchers. They wanted to open it up to non-NASA folks. And that meant other governmental agencies that had objectives in space, and also commercial interests that were able to use the ISS for some sort of economic development. The challenge has been trying to establish a viable nonprofit entity to manage the ISS as a national lab, to be able to open it up to a larger community. Then there's the question of, well, right now the ISS, we've had a majority of the international partners sign up to extend their commitment to ISS until 2020. It's obviously very expensive to have built the ISS and operate it, and the question will be, will the countries have the national will? Will they have the financial resources when it comes time to be able to extend ISS beyond 2020? It remains to be seen if this commercial expansion and the expansion of the national lab will be able to help with that cause. Obviously, Elon Ramon's STS-107 mission was about science. He understood what that meant. The science on board ISS is not for any one individual or for any one country, but it was for the benefit of all humankind. But also the ISS is not only for science, but also is a place for us human beings to notice and understand and share the beauty of our home planet here. The Dead Sea, hurricanes, the glaciers of southern island of New Zealand, the boot of Italy, the sunrises and sunsets that happen every 45 minutes. Obviously, Mount Hermon and the Sea of Galilee. The ISS is what's taken us into the future, the research and science on board, and we don't know what discoveries we're going to find. The one thing we do know is the legacy of the research that's being done on the ISS is going to have definite economic benefits here on Earth. It's going to benefit our quality of life, and it's also going to allow us to seek out answers to things we don't know. We've got a very unique blue ball here called Earth in our solar system. Unique because it has an atmosphere. A very thin and a very fragile atmosphere. So as we look at Israel from space, I have a question for all those young men, sons of Israel in the back there. You know, which one of you is going to be the next Elon Ramon? Not necessarily, or perhaps the Elon Ramon, the astronaut, but what about Elon Ramon, the dedicated husband, the loving father, and a hero to Israel? To all the young women out there, daughters of Israel, which one of you is going to be like the next Ronald Ramon? Dedicated wife, courageous mother, and I think hero to us all. So I'd like to go ahead and thank the Fisher Institute, the Ministry of Science and Technology, and the Ramon Foundation for the opportunity to participate in the conference. I'd like to close with not my words, but the words of the man whose legacy we honor here today with our presence, our thoughts, and our prayers.
Randy, this was really fantastic. You not only showed us your own experience, but I think many people also here in the audience, they've seen all the pictures of the space station. They see the star moving along very quickly and very bright, which is the space station from Earth. But they always ask themselves, what's actually done up there? And you showed us that there's a lot of activity, a lot of scientific and technical results, which also have reflections for benefits here on Earth. And I thank you very much for giving us this information. Thank you again. So I would like to introduce the next speaker, which is Professor Eyal Ben-Dor. He is the head of the Remote Sensing and GIS Laboratory here at the Tel Aviv University. He is one of the global players in his field, and what is his field? It's earth science and environmental science, with particular emphasis on space activities. He is a global player. He's been working in Boulder, Colorado, at the University of Colorado. He worked in the GEO Research Center in Berlin, some of the top institutions in this field worldwide. And he's a specialist in advanced and novel applications. The title of his talk is Hyperspectral Imaging from Space in View of the Nobel Prize. I'm very keen to learn the special view of the Nobel Prize. Professor.
Thank you very much for this kind introduction.
Gentlemen, thank you to the Fisher Institute for your invitation to speak here. When I began to pursue this subject 25 years ago, this was way, way out of the box. And today, I'm really happy to hear in the corridors the words hyperspectral without blinking. People know what it is. People understand the need for it. People also understand that this has a new momentum, and I think today more than ever people need to understand the history of this program in general terms and of hyperspectral imaging, where it was born. In order to know the future, you have to know the past too, and I'm not sure that people deal with it actively alone, that the people who are involved in it actually know the history. I have been privileged to be there when the history was developing, and so I wanted to give a more popular type lecture in order to draw in the younger audience here in regard to a really amazing technology. And so what I'm trying to do here is to give an effect of the Nobel Prize, the most important prize that every researcher aims for, to see how that connects to this technology and to see that perhaps the next Nobel Prize, at least that's what I think, should be focused on this technology. So this lecture will focus first of all on the definition of the HSR technology, what it is. I will give a few very simple examples, and then I will show how this technology, in my opinion, is connected to the two Nobel Prizes in physics, two very important Nobel Prizes, which I'm sure you were familiar with. I'll show you in a moment. And then I will talk a little bit about the history, where it happened, how it happened, who were the people that were involved, how it happened that this history was incidental and not deliberate. And this technology, incidentally, is at the forefront of research. That's also an interesting story. And then I will look together with you at some of the very interesting applications. Space helps us with ground applications and in the laboratory too. We've spoken a lot about that in this conference. And then we will talk about the current status of the technology, and of course we'll talk about the future, where we are, where the world is. And finally, I will try to convince you that there are two very important candidates for the next Nobel Prize in physics. And that perhaps will be the high point of my lecture. So Professor Alex Getz, who was the mentor, is still the mentor, the spiritual father of hyperspectral remote sensing, HSR. This is the ability to collect data from many spectral channels and to create a broad spectral band. This means imaging an object with many cameras, each of which is sensitive to a different wavelength, and this gives us what we call a spectral cube, that has a spectral and a spatial component. If we look at this picture, which is taken from NASA, we can see that every sphere on Earth has a typical spectral signature. The atmosphere has a characteristic signature. The lithosphere has its typical signature. And the hydrosphere, the biosphere, and even the cryosphere, each has its own. That the cryosphere is where there are icebergs and so on. Each has sub-departments, which each has its own characteristic signature, and we'll see this more in the physics of material. We use mainly two sources of energy. The first is the sun, the other is Earth. And both are black bodies that absorb energy. We use this energy. We don't control this energy. And so remote sensing that I will be describing is passive remote sensing, even though we also have active remote sensing. We also have sub-areas, spectral areas, which in professional jargon are known as UV, V, near, SWIR, NWIR, and so on. If we have been doing remote sensing since about 1972, when NASA sent Lancet, then we would be talking about 4 or 5 spectral channels. But imagine that I could increase this to hyperspectral channels, so I get hundreds of channels. And if we look at the bottom graph on the left and on the right, it's the same object, but we can see that the spectral details are much greater. There's much more data there. I'll show you an example. The example is more or less a schematic example of a plant. On the bottom we have multispectral, 6 channels. On the top we have hyperspectral. We can see that very important data gets lost if we go only to this multispectral, and we can see all the important information that we can get with the hyperspectral. We see that there are spectral changes on the graph and very important information that we can use and quantify and distinguish between materials that have seemingly the same color, and we can see how much there is in each given pixel. In other words, we have a spectral fingerprint for each of the components. You cannot make a mistake with it. It does not change unless someone changes the chemistry or the physics. And because this signature is so unique, we can also get the concentration of the material. This is an example that shows a picture of flowers on the left. One of them is, of course, a plastic flower. One is real. And if we look at the spectral range that the eye cannot see, we'll immediately see which is the real flower and which is the artificial flower. This just exemplifies how, or illustrates how advanced this system is that can give us information we cannot see with the naked eye. And there are, of course, many other applications for our lives. As I said, you can see the concentration. If we look at the same place in the graph that changes, we call that the peak. We can quantify it and then cast it on a simulation, on an image taken from a satellite, and we can quantify how much there is of each mineral in each pixel, and we can see how precise that is. So how are all these things connected to the Nobel Prize in Physics? That's the question that we're all asking, and the chair was also very curious to know the answer to that question. So let's look at the first Nobel Prize that Einstein received in 1921, which he received for the photoelectric effect. Today we cannot imagine our lives without the photoelectric effect. In 1921, he won the Nobel Prize for this effect, a very important effect that is an integral part of all remote sensing components. In 2009, 2 scientists from Bell's laboratories in the US, Boyle and Smith, won the Nobel Prize for the invention of the CCD sensor, which is an upgrading of the photoelectric cell that Einstein came up with. And they created a matrix from the cell, and we work with that matrix in every digital camera that each and every one of us carries in our pocket, in our video cameras, and of course in our phone cameras. In 1972, they already came up with this in '69 and only got the prize in 2009. But in 1972, 2 other professors, Getz and Van from NASA, they were aware of this invention, and they said, let's take this invention, and we won't just look at pictures, we'll try to get a spectrum out of this invention. And what they did, they tried to get one side of that matrix for a spatial side, another side for the spectral side. And they took the CCB, and they created a spectrometer, which managed to get the spectral signatures of the Earth, and they put it on one of the shuttle missions with 10 spectral channels, and then they created the first hyperspectral camera, the well-known camera IAS, and we'll look at that in a moment, and we'll see some interesting examples of its work. And these were the milestones that led these 2 scientists to come to NASA and to say, we want to develop an IRS sensor, put it on a plane, and we'll prove that you can see a lot of things that you cannot see with the naked eye and that you certainly couldn't quantify in any other way. But not every good idea is a success, and that's a problem in science. Good ideas don't always succeed, and not everything gets produced, and so you need time. And time isn't enough either. You also need luck. Did this situation exist 30 years ago when Getz and Van looked at the CCB? No, sadly. And their idea almost went into the garbage because a lot of people said, what do I need 2,000 or 200 channels when I can see it on 5 channels? Too many channels isn't good. The data is repeated. It's redundant, and their discovery was almost thrown in the garbage. But ultimately, this is where the technology really began to grow. These are the results of the IAS. The IAS was flown, and they received a spectrum, and they didn't quite know what it was. At the time, there wasn't enough information about these spectral channels, and they went to the Earth and they sampled the land, and they saw that it was a kind of a soil that has an association with gold and silver. So in one of the newsletters they reported this, and Channel 4 in the United States immediately heard about it and came out with breaking news that a very simple method to find gold and silver was discovered. So immediately after that, NASA began to develop what is this called AVIRIS, this airborne spectrometer. AVIRIS was a sensor that is and was, it's constantly being updated. It can get 220 spectral channels at amazing resolution, and today you can say that this AVIRIS sensor has done for remote sensing what the internet did for communications. And in 1965, Getz and Van came out with an article in Science, and of course the articles have increased since then until about 2009. Almost 1,200 articles were published on this subject, and in 2009 there was a big celebration in honor of Alex Getz, who retired, and they summed up this period with a great deal of honor and support for him. Alex Getz himself wrote a paper, and in this paper he notes, he says, don't rest on your laurels. I made an effort. You have to take it further. There's still a great deal that has to be done, especially in space. I was at one of the largest conferences on remote sensing, and I was looking at the list of sessions. We're all familiar with SAR technology, with all due respect. And as you can see, this graph shows a very respectable rise in the area of SAR. It's an interesting, in HSR, and I see a reduction of SAR, and you can see they're going to meet very soon. So it's very interesting to see where the countries, when you put in keywords, you see what countries come up. And in short, this technology is the only one that developed in the civilian world and moved into the defense world. It was first used for geology. Van and Getz were physicists, so it developed from geology, and today we know that there are so many different other applications as shown in this table, but we must bear in mind there is also the military area, which is a derivative of the civilian technology. The civilian technology was a precursor of the military technology rather than vice versa as in most other technologies. And in 2009 there was a very large conference organized by Alex Getz, and there was more or less a consensus that 80% of the applications in the HSR area are still unknown. We know 20% of the applications about which there are papers and have been tested. There is about another 15% of applications that are being tested, but 80 or 75% of the applications are unknown. Where are they? They're in your brains. They're in our minds. They are developing as we speak. And I'd like to go over some of the applications we have in this field. For example, if we want to discover pollution in the urban environment. For example, asbestos roofs, we cannot see them with the naked eye, only if we have a special spectrum. Here we have a picture where we can locate asbestos roofs based on their spectrum. Sea and water, if we look at water, it looks the same color, but there are changes in the water. There's related to the chemistry of the water, to the biota of the water, and this can also be seen using this technology. We can see a mapping of soil, especially if we're looking at the health of soil. With the naked eye, you can't see anything. The farmer has no idea, but this technology helps to see. Americans a year ago completed a crazy project where they covered all of Afghanistan using this technology in order to find energy sources and mineral resources, and this technology showed that Afghanistan has amazing natural resources that are almost untouched. And the moon, in 2009, an American spaceship with a sensor that arrived there with an Indian Lynch, a joint Indian-American venture between the two space agencies, discovered water on the moon. There was a lot of buzz about that. It discovered a small molecule on the poles, but without this technology it could not have discovered it. In agriculture, we can identify stress in plant life. We can see when plants are sick. We can also see in the atmosphere how the atmosphere changes from one moment to the next. Here we have water vapor and how this changes every few minutes in any given time. We can go to the soil. We can use this for soil applications, and I'd like to show you now the aerial applications and how this helps us in the day-to-day. We have here, for example, hyperspectral camera taking pictures of concrete, and using this spectral information we can assess its strength, the strength of the walls. We can use this in the restoration of paintings. We can characterize fakes of Rembrandt and Gogh, counterfeit pictures. And in medicine we can see all kinds of things that a doctor is unable to see, and to save organs and limbs we can identify faces based on the spectrum that each person has in their face and their head. Everyone has their own unique spectrum, just like a fingerprint. We can detect the fertility of eggs without breaking the eggs. We can save a lot of energy in egg incubation. We can also discover counterfeits and forgeries. And from telescope to microscope, we can work with hyperspectrals, and we have a miniaturization of the technology. We can work with very, very tiny sensors and put them in UAVs. And where is Israel here? These are all the countries that are in space today and that plan to go to space. And Israel is, of course, there too, with the Israeli-Italian program to put Shalom in space, I hope very soon. And the Shalom plan is very ambitious, and I hope that it gives us a new dimension for hyperspectral. It combines hyperspectral with ground resolution on a very high level of 10 meters. This has never happened before. There are technological difficulties, but the Israeli industries are very ambitious, and I am sure that they will resolve the issues. And if we were to sum up this lecture, I would say that HSR technology is indeed a well-known technology. It has many, many uses. We are not familiar yet with many of the applications. We still have a long way to go. And here in Israel, we are still a leader in HSR technology, in science and in technology. We are a leading industry in this area. I'd like to go back to the Nobel Prize and say that Greg Van and Alex Getz based themselves on two technologies that received a Nobel Prize, Einstein's technology and Smith and Bone's technology. And so my proposal, in light of what has been written about these people, especially about Alex Getz as a leader, as a trailblazer, a pioneer, as someone who knows how to lead the academia and afterwards the industry. By the way, he opened an industrial Campbell, a small to mid-sized enterprise that very successfully manufactured sensors to conduct calibrations in space. Greg Van is, of course, part of my proposal, and that's why I think that they should receive the Nobel Prize in Physics sometime soon. I hope soon. I will be giving this lecture at other conferences too, and I hope that it falls on attentive ears. I would just like to say one thing to the younger generation. Hyperspectral is thinking in cubes. It is not the cognitive thought that we use every day. It is not what we see in 2 dimensions. We need to add a spectral dimension. It's not an easy thing to do, and it's quite innovative. But if we look at every object from a spectral dimension too, we can go very far, and we can look at other stars. And this dimension it should not be limited only to looking at Earth. If we collect, we can look at galaxies too. I would like to conclude this presentation with Maktesh Ramon. As you can see in this photograph taken from Lancet, Maktesh Ramon is one of the better-known places in the world to scientists working with remote sensor of the soil as a place for calibration of satellites after 10 years. And this has been included in one of the calibration regions of CEOS, and I hope very much that we will be able to use this for our sensors as well soon. I'd like to thank everyone for listening, and I once again thank the organizers for the outstanding organization of this fascinating conference. Thank you.
Thank you very much, Professor Mendel. This was a real eye-opener. I was not aware of all the links between space technologies in hyperspectral Earth observation and all the applications on Earth. Really fascinating, and I wish you all the best in your campaign for a Nobel Prize, and I hope that next year or maybe a few years from now we can celebrate a Nobel Prize in hyperspectral spectroscopy. So with this, we come to the last presentation of today and of this conference. And this is really up to date. It's recent discoveries from the Curiosity Mars rover. It will be given to you by a real insider. And it's not only an insider, it's a heavyweight. He doesn't look like that, but he's a NASA associated administrator for the Science Mission Directorate. He's an eminent scientist, and at the same time, he's an astronaut. He had 5 flights between 1995 and 2009 on Spacelab and Shuttle. He has logged 58 days in space, and he has also nearly 60 hours in extravehicular activities, in spacewalks. He was appointed as NASA chief scientist in a previous appointment at NASA. He is an eminent astrophysicist, specialist in cosmic ray and X-ray, also in exoplanets, And in addition, he's a passionate mountain climber, and he's the only astronaut who ever climbed Mount McKinley, the highest mountain of North America, with 6,100 meters. John, you have the floor.
Thank you very much. It's a pleasure to be here, and I've had just a wonderful setup from all the previous speakers who have provided a lot of background for things that I'm going to talk about. But I'm going to try and give you a bit of an introduction to Mars. And if you heard Charlie Bolden, our NASA administrator, my boss's talk yesterday, he said that when he was selected as an astronaut, he believed that his group of astronauts would be the astronauts who would go back to the moon and that might have a chance of going on to Mars. My class was also told the same thing, that we would be the astronauts that would be going back to the moon and to Mars. And I know for Randy Bresnik's class, when he arrived, we told them the same thing. And, you know, I truly hope that it is not too long before, you know, some of you, the next Israeli astronauts, women and men, will join the astronaut corps and will be told that you will be the astronauts to go on to the moon and Mars, and actually will. I think that's a major goal of our space programs around the world, and it will be a worldwide effort. But specifically, I want to tell you about the most recent results that we have on Mars, but to set some context, referring to the earlier talk on astrophysics, you know, Mars is a planet in our own solar system, but we've discovered many, many more solar systems. From the Kepler satellite, the NASA Kepler satellite that you saw staring in this region of the sky near the constellation Cygnus, we've seen thousands of other planets. Many of them are the size of Earth, a little bit smaller, a little bit bigger. Some of them are several times bigger than the Earth. There are a lot of planets that are the size of Neptune and Uranus, many that are Saturn and Jupiter sized. But the conclusion of these results that we've seen is twofold. One of which is that 1 in 6 stars that are like our sun has an Earth-like planet, Earth-sized planet around it. Now, we haven't found Earth 2.0 yet, one that is in a habitable zone and that has about the same size and mass of the Earth. But I think it's only a matter of time. But the other conclusion, I think, is even more meaningful to all of us who like to go out and look up at the sky at night. And that is, if you go out on a dark Tel Aviv night, maybe a little bit outside of town, and look up at a dark sky, you'll see lots of stars, hundreds of stars. And one of the conclusions from the Kepler satellite is that nearly every one of those stars has a solar system around it, several planets. And I think that's very exciting, because who didn't wonder whether every star has a planet, or if there are any planets, or if anybody's out there. And I think that's the grand question. You know, are we alone? Is there any other life out there? And so that's what drives me. I think that's something that science will be able to answer in the not-too-distant future. And in our solar system alone, there are many places that life could exist. Certainly on Earth, we know there's life. I often wonder whether there's intelligent life on Earth, but that's a different lecture. But we have a wide variety of planets, a very diverse solar system. We have an orbiter around Mercury right now called Messenger, and it's clear that Mercury cannot support life from the Messenger measurements. It's like that planet that was just 0.04 times the distance from the Earth to the Sun around Alpha Centauri. It's too hot. Life as we know it couldn't exist there. And then we have very cold, icy planets, you know, out at Uranus, Neptune, Pluto, and we have the New Horizons spacecraft on its way to Pluto for a rendezvous in 2015. So we're looking forward to that. We have the Juno spacecraft on its way to Jupiter. Around Jupiter, Jupiter has its own little solar system, and there's a wide variety of planets, including Europa, which may have 30 kilometers of ice, but underneath a warm, salty ocean, warmed up by the tidal squeezing of Jupiter, the big tides. And so that's a place where there could be life. But it would be microbial life, not a place that we could live necessarily. But Mars is different. Mars is very much like the Earth. It's smaller than the Earth. The gravity on Earth is only about 3/8 that we feel here on Earth, the pull of gravity. But Mars does have an atmosphere. And in the past, as I'll describe, Mars could have been very Earth-like. This is a picture of Mars that shows the polar ice cap on the south, and very much like Earth, Mars has polar ice caps. And we've actually known that Mars has current water. And we've known that for quite a long time. And this is also a chance for me to show a Hubble Space Telescope picture because I'm a known Hubble hugger, both figuratively and literally, having gone up and serviced the Hubble Space Telescope. But also near the top of the picture, you can see, if I can get a mouse here, you can see that there's some haze. And those are actually clouds, and there are carbon dioxide and water ice clouds. So Mars is very much like Earth in that way. Now, Mars mostly is a very dry planet when we look at it. So where did the water go? And a lot of the water must have escaped to space in the distant past, and I'll describe that. But even today, there's an enormous amount of water, and so this isn't quite hyperspectral, but it's a multispectral map, and it shows from the emission of neutrons, the distribution of current water underneath the surface of Mars. And so this map shows, if it's purple, a very high concentration of water underneath, and over on the left where it's red, on the map of Mars it shows very dry conditions. And so where is that water? Well, we've had satellites with ground-penetrating radar that have shown us that underneath the surface of Mars, in the north and down to about 60 degrees, and the south and up to about 60 degrees latitude, an enormous amount of water underneath in glaciers. And that water could be accessible. And the further south you go, the more water there is. Just a few years ago, we landed the Phoenix lander near the North Pole, and we were hoping to be able to dig a little bit and see water. And when it landed, the rocket exhaust blew off the dust, and we had landed on a large water ice glacier. And so water is something that we know is on Mars today. Occasionally, from our orbiting assets, we see that a meteorite has hit Mars, or a meteor has hit Mars, and where it causes a new crater inside in the upper left there, you can see the white. That's actually water ice. And so the dust has been blown off, and at the bottom of that crater is ice, accessible near the surface. And we see that all over the surface of Mars. We've seen quite a few of these events, at least 5 or 6 events at various latitudes where meteors hit the Mars and it excavated fresh ice. Another thing we see is in gullies, steep gullies on the sides of some slopes, and this animation shows you a series of pictures taken weeks apart during the summer on Mars, that something is seeping out of the sides of these steep gullies and flowing down the slopes. And the leading belief is this is salty, briny water, and its salt depresses the freezing point, and so it's able to survive in the roughly 0 degrees C and very, very low atmosphere, 1/100th of our atmosphere. Normally it would evaporate instantly or sublimate, but because it's so salty, it survives long enough to flow down, and that may be what is creating these gullies over long periods of time. So that's modern water. It's believed that perhaps only 500,000 years ago that the Mars surface may have been covered with an enormous amount of water. In geologic history, by looking at the minerals and trying to date Mars, we think that somewhere around 2 to 4 billion years ago, Mars was a warm, wet planet. Had water on the surface, it had clouds, it had rain, and we see that evidenced in the rock through spectral measurements of the minerals and the conditions, and estimating the amount of water that we see. Now we see that because we're comparing it to Earth. So I have to give you, one condition, that we're trying to understand Mars the way we understand Earth. Mars is a very different planet, and it's likely to surprise us once we understand the geology. We're still just beginning to explore Mars. But it's believed that somewhere between 2.5 and 4 billion years ago, there were many instances of warm, salty seas, flowing water, some very large episodic events, floods, and we see that all over. And we see that in those sulfates, in the clays, and in some of the iron oxides. Now, Mars is a red planet. That's the iron oxide. Any oxygen has been taken up by the rust in the rocks, essentially. And that's the modern Mars that we see. So here are some signs of that ancient water. We see gullies that can only have been created by flows of fluids, presumably water. We see places where there was standing water. We see these things that are called blueberries. We discovered this from the Mars exploration rovers, Spirit and Opportunity. Opportunity found these little rocks that contain minerals that are created when there's standing, warm, salty water. and we see lots of evidence of flowing water. And just recently, in the lower left here, we're seeing gypsum in the cracks or veins in rocks. And this happens when warm water flows repeatedly through these cracks. Now, that's a theory that it's gypsum, but we're about to find out. This is a crater that was seen by Viking in the green on the upper left. On the lower right is a color image from the Viking, and you can see that enormous amounts of water flowed around these craters sometime probably 2 billion years ago. And the green crater is actually named Lod, and it's a town that's near the airport, just close to where we are. So I'd like to take a quick poll. How many of you think this is one of our new pictures of Curiosity from Mars? I must have one taker. Okay, good, I have one taker. No, in fact, this is Israel, and it does look very much like Mars. And here's a picture that we have now from Curiosity on the sides of Mount Sharp. This is the mountain in the center of the crater. And so there are many parallels to the Earth and Mars. Here's layers in the Maktesh Ramon cliffs. We just saw a picture of that in the Negev. In the earlier example of hyperspectral calibration. This is a great place to study the Earth to try and understand Mars. And that's what our planetologists, our planetary scientists do, and our geologists do. This is a zoom image of Mount Sharp. This is where we want to go. We want to go to those sedimentary rocks, those layers, and try and look to find out if 2.5 billion years ago Mars had the conditions, the flowing water, carbon compounds, and the structure that would have supported life. Did Mars have life? We may or may not know from Curiosity, but this will get us one big step towards finding out when Mars was warm and wet, were the conditions possible for life to exist. In the desert, of course, we know life can exist, and one of the things that intrigues me is that especially here in Israel, you've learned masterfully how to bring life to the desert. And I hope someday that the future astronauts will be able to go to Mars and bring life to Mars, as you see here in the Negev, and also I think on Mars someday we will have large greenhouses. Certainly we have lots of carbon dioxide for the plants for respiration. So how do we understand all of this? And I think I don't have to say very much about this because of the previous talk, but we fly over with reconnaissance satellites that have multispectral. Hyperspectral would be great. We have instruments that we land on the ground, and then we try and compare it to what we know here on Earth. We've sent a number of rovers to Mars. We sent the Sojourner rover to Mars. It was about so big, about the size of a microwave oven. Then we spent the Spirit and Opportunity rovers to Mars. They were a little bit larger. And now we've sent the Curiosity rover, which landed last August, to Mars, that's about the size of a small car. And with each of these, we get more mass to Mars, larger rovers, but more importantly, much more sophisticated science. So where did we go? In the Viking era, we sent 2 Viking landers. Their purpose was to discover whether there was life on Mars, and they determined, well, we don't really know what they determined. It was a very ambiguous signal, but we concluded that Mars was a dry, lifeless planet, and for over 20 years we stopped exploring Mars. But from continued interest and some of our satellites, we decided to go back with ever more capable missions, and we've been discovering things quite remarkably ever since. We sent as I mentioned, we sent the Phoenix near the North Pole. We've sent Curiosity and Spirit. But we've spent Spirit and Opportunity. And in Spirit and Opportunity's case, we had many, many places that looked interesting from orbit to send the rovers to try and see if conditions were right for life. And we picked 2 of the most boring spots we possibly could. Boring in the sense of safely getting them to the surface. With Curiosity, we took a different track. We designed the system for precision landing and sent it to a very challenging spot. And this picture shows some circles. The outer circle is the error ellipse for landing Viking. The next smaller one is the Pathfinder rover. The sort of longer ones were Spirit and Opportunity, the MER. Phoenix was a little bit better, but the Mars Science Laboratory, which is the smallest one, is our precision landing. And it's precision landing because in the background you see the crater that's about 80 kilometers across that we wanted to put Curiosity in. In the center is a very high mountain, and we didn't want to hit the mountain. We wanted to have Curiosity rover, not Curiosity crater. And we wanted to pick a spot that very likely was interesting and the closest we could to some clay material that indicated that there was water some billions of years ago. So here's how we did it. This is called the 7 minutes of terror and triumph.
Things are looking good. Coming up on entry. They're looking good. Coming up on entry. Vehicle reports entry interface.
1,000 kilometers an hour.
We are beginning to feel the atmosphere as we go in here. It is reporting that we are seeing G's on the order of 11 to 12 Earth G's. Reversal 2 is starting. We are now getting telemetry from Odyssey.
Eventually, at about Mach 2, we put out a parachute, which is also a very hard thing to do.
The parachute is deployed. We are decelerating.
Then we got rid of the heat shield.
Separated, we found the ground.
Then we did a really crazy thing. Once we were slow enough, we dropped the rover.
Standing by for batch cell separation.
At which point we fired some rockets.
We are in powered flight.
And kind of like a Harrier jet, we slowed down.
We're at altitude of 1 kilometer descending.
But the rocket was on top, so we couldn't land.
Standing by for sky crane.
So once we were going slow enough and we were close enough to the ground, we lowered the rover on a sky crane, lowered the wheels like landing gear, slowly, 0.7 meters per second, put the rover down, cut the wires, and then flew away.
We're safe on Mars.
And what you really see there are very happy people, but it was disbelief that it all actually worked.
Got thumbnails.
And then we got the first pictures just a few minutes later. And in those pictures, we actually saw a plume of dust from where the sky crane landed. So we're on Mars. Now this was an event that we were very excited about in the control room, but millions of people around the world were also watching. We had thousands of people in Times Square. We had over 100,000 people in India watching. We had tens of thousands of people around the United States. Millions of school children in American camps stayed up watching. And I think for many of those students, this event of landing on Mars with this great Curiosity rover will be as significant for them as the Apollo landing was for me and many people of my generation. And why is that? And we heard that again yesterday in one of the discussions. When I was growing up, kids were interested in space and dinosaurs, and that was the big thing. Now, more so, kids are interested in robots and dinosaurs. And not only that, Curiosity is a robot with a laser. And so this is a very popular thing around the world. And so Curiosity does in fact have a laser. It's part of a chemistry camera. We can basically vaporize the rock and look at the emission from the rock with the camera up on the mast, and that tells us about the composition. We have instruments that determine the weather. We have many, many cameras. I think there was a total of 17 or 19 cameras, some of which are a narrowband, a telephoto camera, wide-angle camera. Some of them are used for navigating. We have an alpha particle X-ray spectrometer that allows us to illuminate rocks with X-rays and see the emissions to tell what kind of minerals. We have a number of experiments inside the sample analysis at Mars that has a tunable laser spectrometer, a mass spectrometer, a gas chromatograph. I'll show you some results. This tells us what the chemical abundance is, the molecular abundance, and the structure of and isotopes of the instruments. We have an instrument that looks down and scatters neutrons to tell us what the hydrogen content of Mars is. So many different instruments. It's a true science laboratory on Mars. It's also a very international collaboration. We have contributions from many, many countries, including Israel. And Israel has contributed both to the Curiosity rover and to the Mars Reconnaissance Orbiter flying overhead, which helped us to determine where to go. Specifically, Rykor, a company in a kibbutz here in Israel, produced the cooling system for one of the detectors, a crucial piece of the Mars Science Laboratory and the Mars Reconnaissance Orbiter. So Curiosity arrived on August 6th, so we have almost 6 months of roving on the surface. This is a self-portrait that was made by stitching together many images from a camera on the end of the robot arm. And this is just a picture of the landing site. So from the Mars Reconnaissance Orbiter flying overhead, it has 30-centimeter resolution. We've been able to image Curiosity and its path. We see where the sky crane landed in the upper left, and you can see that the soil has been disturbed from the rockets. The heat shield which we deployed continued downrange, and we see in the lower right where that landed, and we also see the back shell on the parachute. In fact, it was an amazing feat that the Odyssey spacecraft, another NASA spacecraft, flew over and was able to take a picture of Curiosity while it was still on the parachute. And we can image the individual gores of the parachute as it was going down. And that actually gives us good engineering data about the performance of this parachute. So this is the hyperspectral, not quite its multispectral picture that we took going over the site before we decided on landing there. And what we see is that there's this Peace Vallis, which looks like a river coming out, that spreads out into an alluvial fan, and that indicates that there was water flowing out. And there's indications of clay in that area. And then we see some different colored material that we're just learning about now, and then evidence of water flowing. So we wanted to put Curiosity down in that ellipse, and there's a small plus mark showing where we landed. And so our hope was to land somewhere near where there might have been water, go investigate that, and look at the minerals and the morphography, the structure, to see if it's someplace that might have had running water that might have supported life. So when we landed, we looked around and started driving, and we don't drive very fast. We came across these rocks that kind of look like broken sidewalk. These are called concretions, like concrete, and there's several features that are very interesting. First of all, that you have some kind of cement holding pebbles together, and then you have, where there's erosion, a lot of pebbles lying underneath, and the pebbles, both on the ground and in the rocks, are rounded. And in fact, this is characteristic of a stream bed, a fossil stream bed. So we really hit the mark with landing Curiosity. A little bit of luck, a little bit of skill, but we landed in an ancient stream bed. And so we haven't gone very far because the place we landed turned out to be really exciting, but we're still trying to get to other places. This is just a blow up. On the left you can see, and there's a scale of 1 centimeter, some of these rounded pebbles, and on the right you can see basically a relatively current riverbed that's had water running in it for some thousands of years. We have a robot arm on Curiosity, and on the end of that arm we have the tools of a geologist. A geologist would carry a magnifying glass with him, a loupe, and so we have a Mars hand lens imager. We have scoops, we have brushes, we have the alpha particle spectrometer, we have some handling equipment, and we have a drill. And all of these are what we're going to use to help investigate the rocks, and the scoop will pick up samples and bring it into the instruments that are inside of the rover. So this is the hand lens imager. This is one of the basic tools, a rock hammer and a lens. That's what a geologist on Earth would do if he were on Mars. And so we've gone up to some of these rocks, we've been able to image them in great detail, and this is the first step in understanding the structure of Mars. Inside of the sample analysis at Mars, as I said, we have very sophisticated instruments to be able to analyze the isotopic ratios, the atomic composition, the molecular composition, the molecular weight, and the gas content of the Mars atmosphere, all in this instrument. Now, normally, these kind of mass spectrometers would fill several large laboratory benches in a modern laboratory, and you'd be able to tweak them and change gas flow and all these kind of things. And we had to shrink them all down into a very small box, and this is one of the great achievements, and be able to have it survive the trip to Mars. So this is what the Mars atmosphere looks like. It's not that much different than what we saw on Viking in the 1976 time frame, but these are the most precise measurements we've ever made. And one of the big questions is there methane on Mars? Now on Earth, cows are one of the biggest sources of methane. We don't think there's cows on Mars, at least not yet. But there were some observations from a ground-based telescope, a NASA telescope on Hawaii, that indicated methane on Mars. Now, it was very difficult to look through the Earth's atmosphere, which has lots of methane, and detect methane on Mars. So this was one of the prime objectives of the mission. Mostly we see what you expect: carbon dioxide, argon, which we also knew about, a little bit of oxygen, a little bit of carbon monoxide, and we also see nitrogen. This confirms the nitrogen measurement. I think this is very exciting for a number of reasons, one of which is eventually when we get humans, we're going to need that nitrogen. We don't have to carry it with us. Nitrogen is good for fertilizer, but it's also the major constituent in our atmosphere, so if we want to have a relatively normal atmosphere inside of our space habitats, we'll need that nitrogen. But we didn't see any evidence of methane. Now, we were able to calibrate that methane, calibrate the measurement of the methane, upper limits, because we brought some methane with us. We brought a sample of Florida air, which has lots of methane, and we analyzed that, and we got a very strong methane signal. When we then brought in the Martian atmosphere, the methane signal got lower. We brought in more atmosphere. That methane signal got even lower. So we were bringing in, and we took the difference, and it's consistent with no methane. Now, Curiosity is a 2-year mission, 1 Martian year, 2 Earth years. And there's a good possibility that if there's methane, it may be associated with seasonal changes. As we get into a warmer and warmer summer, methane may come out from geologic sources or frozen underground reservoirs, and so we're going to continue to do these measurements. So I think the methane story is still open. This is sort of the equivalent of the human footprint on the moon. This is the Mars scoop print on Mars using the Chimera scoop, and we've brought some of that soil in. We've done X-ray diffraction now to tell what kind of minerals. On the left is a picture of an X-ray diffraction instrument on the ground. We had to make it about this big, small suitcase size or briefcase size, and we've actually been able to use that here on Earth. So this is one of the first X-ray diffractions ever done on another planetary surface. It shows the patterns of rings characteristic of the crystal structure. So this isn't just looking at the components of the molecule, but actually looking at the crystal. That's what tells us what mineral it is, and so we're able to analyze what kind of minerals. That was a feldspar, which we also see here on Earth. We've also been able to look at the atomic and molecular structure, and we see oxygen and various isotopes. We see hydrogen sulfide, that gas that makes swamps smell like rotten eggs, sulfur dioxide. We also see cyanide and other nitrous oxides, and so we're starting to build up our inventory of what kind of things are in the rocks when we decompose the rocks. We see chlorine, and that's an indication there may be perchlorates in the Martian soil, and that's long been suspected. Perchlorate is actually aluminum perchlorate is what's in our solid rocket motors on the space shuttle, but it's also something that bacteria on Earth use as a food. And anywhere you have water, energy sources like the chemical reactions with perchlorate and organics on Earth, we find life. And so this is somewhat tantalizing already. These chlorine compounds we see in a lot of different forms. In this case, they are in combination with parts of organic molecules. We're not sure yet whether these organics are provided by contaminants in the rover yet, but over time we'll be able to see whether these methane compounds are Mars-based or whether the chlorine is reacting as we heat up the samples. But we're finding that in an area that we call Rock's Nest. We also have a tool as we go up to rocks to be able to brush them off, because the outside is weathered both by wind erosion and solar radiation, and so just showing that tool in work. We're still learning how to drive the rover and use all of these tools. So far you might say, well, you've been there for 6 months, you must have gone many, many kilometers by now. We've gone about 730 meters. So this is a very slow rover, but it's much more capable than the Spirit or Opportunity. And one of the reasons we haven't gone very far is because we have 400 members on the science team. And the chief scientist, John Grotziner, a professor at Caltech, has to herd all of these cats, has to manage all of these scientists, every one of which wants to stop wherever we are and look at the local rocks. Now, a trained geologist on Mars, using their brain, using that hyperspectral brain that you heard about, would cover that 700 meters in just a few minutes, walking by all the uninteresting things, going, basalt on Mars, who would have guessed? Well, of course we knew about basalt on Mars, so they would walk by those rocks and only stop at the most interesting sites, the ones that say, we're in an ancient riverbed, or wow, that rock looks like a meteorite, it doesn't look like it's Martian, I wonder if it's a piece of Earth, which is very likely to find Earth meteorites on Mars. And so we're stopping at a lot of places, learning how to drive the rover, and being very careful, because if it gets stuck or it breaks, Randy Bresnik isn't there yet to fix it. We got to work on that. So this is where we've been driving. We're eventually going to go up the slopes of Mount Sharp. We're trying to get to a spot about 7 kilometers away where we see some really interesting sedimentary rocks in the telephoto lens. That's going to take probably a year. I asked John Grotzinger. He said he could be there in an hour. Because on Mars you can jump like we do on the Moon. So maybe it would take him 2 hours, but we'll have to try and get him there. So the point that we're at now is called Yellowknife Bay. It's definitely an area where there's water. We see lots of evidence of that. Here's some sedimentary rocks that we see that we're going to go investigate called Shaler. And we also, on the hand lens imager, have some white light LEDs and some ultraviolet LEDs. So we actually are starting to investigate Mars at night too. We're able to run day and night. The previous rovers have all had solar power. Curiosity has a plutonium power source, radioactive thermal generator, which charges a battery. So it can run day and night. So typically we drive during the day when we can see well. At night we do the science analysis and telemeter the data. But we can do some stuff at night that you can only do at night to see if there's fluorescence of some of these minerals. And it's the first time we've done that. So in Yellowknife we've looked for the drilling sites that look most interesting. And we've looked and we've seen cracks in the rocks that have these minerals that appear to be something like gypsum, where on Earth it's formed by water percolating through the rocks, warm, mineral-rich water. And so we've actually placed the drill now on a spot that we want to drill. Now the drilling will cause us to grind up the rock, and then we'll be able to take that rock dust and put it into the SAM instruments, the sample analysis instruments, and then do the analysis. Right now what we're doing, I mean literally right now, we've got the arm there, and the arm is sitting there overnight so that we can see how much stress there is building up in the arm, because what we don't want to do is break off the drill bit. Anybody who's pushed on a drill too hard knows that if you get a little off angle, the drill bit can break. And it may take a while to drill. It may take several days to drill into the rock. And the temperature on the surface of Mars during the daytime is actually quite nice. It's about 0 to 3 degrees C. At night it goes down to minus 60 to minus 70. And the arm changes length by about 3 millimeters during that time. And so we're learning how can we move the arm so that we're very safe in this first drilling, and then we'll learn about subsequent drilling. So we're doing load testing right now. So that's the most up-to-date. Now some of these instruments, like the ChemIm instrument, we've actually miniaturized, and we've been able to use it for other purposes. For instance, analyzing the paint in King Tut's tomb. It's also been commercialized to look at counterfeit drugs in a very quick process, so people can carry it around to pharmaceutical companies or to suppliers and make sure that the drugs have the right purity and the right contents. So what's next? That's the big question about Mars. Not just curiosity. I've told you about that. We're going to continue to explore. We're going to try and get up the flanks of Mount Sharp. But what's next for the Mars program? As some of you may know, our budget is under some pressure in the United States, and our budget for future Mars exploration was reduced. We got a lot of input from very important people about this. This is from Fisher. He says, "Dear NASA, I don't want to end Mars exploration. I want to go to Mars, and I'm 6. 6 years old is probably about right. He's maybe just about the right age to be the first person to go to Mars or somebody to go to Mars. And we definitely are listening to Fisher. So this is the strategic plan that I was able to announce last December. We have these operational missions. We have 3 missions in orbit, Odyssey and Mars Reconnaissance Orbiter. They help us with communications relay and also to study the surface. In cooperation with ESA, we have the Mars Express. On the surface, we have Opportunity rover, which is still going. Phoenix is already complete. Spirit is complete. It's stuck and not working. And Mars Science Laboratory. Mars Science Laboratory, as I said, is a 2-year mission, but it could last for 10. This year, we're launching the MAVEN observatory. It's going to enter Mars orbit and study the upper atmosphere, and specifically, how does gas leave the Mars atmosphere? How is it either blown off by the solar wind, lost to space? And that will tell us about the current history of water as we see water vapor leaving, but also give us an idea of how the Mars atmosphere works. In 2016, we're going to land a mission called InSight. It's a single-station geophysical monitoring station. It'll have a heat flow experiment and a seismometer and a weather station. And in combination, that will tell us about Mars' interior. We've never studied Mars' interior so far, so we don't know whether it still has a liquid core. And we'll use earthquakes and meteorite hits and the ringing of the planet to study the structure of the interior. How thick is the mantle crust if it has the same kind of structure? In 2016 also, we're participants with the ESA ExoMars program and their Trace Gas Orbiter. We're providing support for that mission and the communication hardware. And in 2018, we're participants again with ESA in the lead on the ExoMars lander. We're providing part of the Mars Organic Molecular Analyzer, which is one of these science instruments that will tell us about organic molecules on Mars. And we're very excited about that participation. And then in 2020, we'll land another rover very much based on the Mars Science Lab chassis, this very capable system. And we've just started this week looking at what kind of science. And it'll be community-competed science. And the international community is invited to participate. And that process will go on for about a year, and we'll have an announcement of opportunity then for what instruments will go on there. But it will be based on the same technique of entry, descent, and landing, and then roving as we have on Curiosity. The future beyond that, what we're trying to do at NASA is to take our Human Exploration Division, our Technology Division, and our Science Division, which I lead, and look at the current intersections. Where are we working together now? So for instance, on the Mars Science Laboratory Curiosity, we have a radiation detector that's very useful for science, but also was operating in the cruise phase when it left Earth all the way to Mars, and it's now operating on the surface. And it came out of our Human Exploration Division, and it's telling us about what kind of radiation future astronauts will experience on their way to Mars and on the surface. We had some instrumentation on the heat shield to tell us about what it's like to have a very large heat shield entering the Mars atmosphere at 13 kilometers per second, looking at trying to get things like a capsule or a spacecraft down through the Martian atmosphere. And with each of our missions, we want to build on that so that in the future we have a much larger intersection, but cooperation between human exploration and science. Because my dream is when we send astronauts, women and men, to Mars, they're going to be planetary scientists and geologists, and they're going to go out and explore Mars. So that's, I think, our future on Mars. This is actually a picture of Jack Schmitt, an astronaut in 1972 and a professional geologist on House Rock. And through the wonders of Photoshop, I've colored it to be an image of what we might see on Mars, hopefully in 20 or 30 years. 20 is probably a little bit ambitious, but I think within 30 years it's possible. So with that, I'll close. I'd like to thank the Fisher Institute. I think this has been an incredibly exciting gathering throughout all of the days, and certainly the talks in the science section. And I'd like to just end with shalom.
Congratulations, John, and thank you very much for sharing with us these exciting and very new measurements that you achieved with this new instrument, with the Curiosity rover. And I wish you all the best for the future and for many, many more results of high quality and very high excitement. I would like to thank all speakers of this session, and I hope I didn't promise you too much. This really was an exciting session. And I would also congratulate the organizers of the conference for picking such an excellent set of speakers. And with this, I hand over to and thank you very much.
Thank you very much, Professor Feuerbacher, for your wonderful chairing this magnificent session. All the presentations that you see, that we saw from Randy and John was not a science fiction. This is real stuff. So thank you very much. I would like to invite General Bodinger for a few concluding remarks, and immediately after that we have a reception in the lower level. הרצל, בבקשה.
To all our guests, bear with me. I will speak in Hebrew, because I intend to address the youngsters in the upper level of the hall. So, Erev Tov lekol haorchim
So good evening to all the guests and to all the local attendants as well. Dan Wojtkowski, former commander of the Air Force, and David Ivry, the founder of the Fisher Institute and also former commander of the Air Force. We have just concluded 2 fascinating days of the Ilan Ramon Space Conference commemorating the crew of the Columbia who died 10 years ago in the Columbia tragedy. I want to talk to the young people in this audience. So, to you, dear youth, mankind is an intelligent species which has come from Northeast Africa. It was always a curious species, always trying to find out what's beyond the horizon, what's beyond, what's over the rainbow. Thus, human beings traveled north and then spread to the east and to the west over the continents until they finally got to the sea, the end of the dry land. In order to push forward there as well, they developed the first sea vessels, marine vessels. At first they only sailed near the shores, and this is how space exploration developed as well. At first only around the Earth orbit. Later on, seafaring vessels were able to cross oceans, and when it comes to space, the next step was to draw further away from planet Earth. For all this daring and ambition, we need to pay as well. So who was paying for it? In 1492, Columbus sailed with 3 ships to America. The money was given by the Spanish royals. And then afterwards, Sir Francis Drake was sent by Queen Elizabeth I to circumnavigate the Cape and Cape of Africa, and when he sailed through the Drake Straits, he lost 4 ships and was left with 1 alone. Conquering the seas cost many lives and many ships, and when it came to space, the same thing happened. And in parallel to the seas, flights through space also left Earth orbit and started flying towards other celestial bodies such as the Moon, Mars, and who knows what's next. I have looked at the historic documentation of the preparation to launch Atlantis, the last space shuttle, staying in space for 2 days and then coming back to Earth. The countdown, the launch and the re-entry are always exciting and thrilling, but side by side with the thrill of watching that last voyage again and again, which closes off the era of the space shuttle. It's interesting to read the comments around it. Many words of encouragement, but also a lot is said about wasting resources on ego flights, against show-off flights, and there are calls to invest all that money in developing medicine, for example. And this is where I'd like to point you at the 150th anniversary for the first underground line in London. If you read what people wrote at the time, many were very much against that redundant adventure. Obviously, as we know, it is a great success. It was a great success, and now there are underground train systems all over the world. There are many such examples of all kinds of inventions, and I have a separate talk about that. Continuing to conquer space is an ongoing need, and space research will continue. There will be more spacecraft going into other places, and the youngsters will probably see all that. I would like to conclude by extending my heartfelt thanks to all the guests from abroad who came here and the organizers and producers who organized this wonderful conference, our supporting sponsors, Asaf Agmon, the Director General of the Fisher Institute, who supervised everything. Yes, definitely. And I would like to express my wish that we will all see you, that we will all meet again in the next conference next year. Thank you very much, and good evening.